let's look at a few more aspects on premixed combustion. We will primarily be looking at flammability limits, and this would lead to looking at quenching and ignition. So these are things that we will start looking at. We will try to do this as quickly as possible because we just don't have too much time to dwell into these. The second thing is you can understand that these are typically unsteady phenomena, right? We are talking about the flame quenching near the flammability limit because it runs out of one of the reactants, or it gets quenched because of a thermal heat loss, or the ignition again is a transient phenomenon, and these are things that are not very well understood, and it is heavily kinetics dependent. So it is not amenable to simplified analysis that works quite well, except for in a qualitative sense. So this is kinetics dependent. So what are we talking about as far as flammability limits is concerned? We know, for example, that if you now try to plot the laminar flame speed versus the equivalence ratio, you have a curve that is having a maximum somewhere in the middle, a little bit past equivalence ratio 1, and then it falls down and then it stops at some point. That means it is not really going all the way down to 0. It is stopping there, which means that you now have a fuel lean limit and a fuel rich limit, right? So this is fuel lean limit, and this is the fuel rich limit. This is typical of most fuels. The question then is, what happens as we try to increase let me go back and say this is sometimes referred to as the lower limit, and this is sometimes referred to as the upper limit. Lower and upper meaning different values, the lower value of phi and the higher value of phi, or lower value of fuel air ratio or fuel oxidizer ratio versus higher value of fuel air or fuel oxidizer ratio. Now what we are interested in is trying to find out what these limits depend on, and mostly what we are talking, the mixture ratio obviously is the question. So the control parameters in any premixed flame are the mixture ratio, the temperature, and the pressure. So the question here is, what is the lean mixture ratio, lean limit mixture ratio, or the rich limit mixture ratio depend on? That means you need to be looking at what is the dependence on temperature and pressure. So the answer to the initial temperature of the reactant mixture, how it's going to affect the fuel lean or fuel rich limit, is typically linear. So the flammability limits vary. I'm saying vary instead of saying increase or decrease because one of them increases, the other one decreases. Vary linearly with initial temperature, right, that is enlarge as temperature increases, right. So enlarge as in you can now expect as you increase the temperature the curve to go like that in a linear fashion. And since this curve is not necessarily symmetric about phi equals 1, this gap is not the same as this, right. So typically this linearity is more steep with fuel rich limit, so more steeply for rich limit. In fact this particular picture is a little bit wrong in that sense. So you need to have a larger increase in the upper limit when compared to a decrease in the lower limit. So that's what I meant by saying vary, as in the upper limit increases further and the lower limit decreases further. so more steeply for the rich limit than the lean limit. So what we are talking about as limit is, again to emphasize, it's the equivalence ratio or the fuel air ratio, fuel air mass ratio. So if you now think about a linear variation, so you should be able to now estimate, like for example at 300k, if you have a lean limit like this, and I know how this variation is in terms of like what is the slope of the line that is connecting the temperature with the lean limit, I should be able to predict what the lean limit should be as you now advance your initial temperature to, let's say, 400k, right, how it should decrease and so on. Okay, now the more interesting thing is the pressure dependence. Okay, so the pressure dependence is more significant. The sense it's not so straightforward, and nonlinear in some regimes and insensitive in some other regimes. So particularly nonlinear for fuel rich limit at low pressures. So it's sort of like where we are in the pressure equivalence ratio graph. So if you now look at pressure and equivalence ratio, you're going to get a curve that is somewhat so you have a less sensitive variation with on the lean limit with pressure. That means for a wide range of pressures you pretty much get about the same limit here or a mild variation, and that's not really the case with the rich limit. So here we are talking about phi, and then there's like a wide variation where if you now go to a pressure that is below this limit, it doesn't matter what your equivalence ratio is, it's going to be like a flat curve. So this is your flammable region, and this is your non-flammable region. You got to be careful in reading texts on this. For example, I think the conventional British English is if you now say inflammable, that means it burns. It's not a non-burning thing, right? That's the reason why we use the word non-flammable rather than inflammable. Inflammable actually means it burns, so that means we should write that here. So to avoid the controversy, just use flammable and non-flammable. So now this is again, as I said, it's kinetics dependent. So here we could show, I'm not going to get into this now, this is actually because of second order kinetics at low pressures, and now it becomes linear. So here it's a nonlinear part, and then you now have a first order at higher pressures. Again, what are we talking about for the range? So somewhere in here we are looking at atmospheric pressure. Okay, so we are looking at above and below atmosphere, and many times for this part of the graph we would probably look at more like a linear scale, whereas that part of the graph you would look at a logarithmic scale, because you could, strictly speaking, even think about like pressures that are going up to 100 bar or even more for practical applications, right? And subatmospheric pressure is like between, not exactly 0, you don't go to 0 pressure, but let's say 0.001 and 2 up to about 1 atmosphere. So you could go over there, the subatmospheric range. Of course, what we are talking about, this is for typical hydrocarbons, keep that in mind. The other thing that that is going to lead us to the next topic that we want to talk about is the determination of the flammability limit is going to depend on the duct diameter. Okay, so one of the things that we were talking about is having a duct in which you allow for the flame to propagate, but you now progressively make the fuel the mixture leaner and leaner and leaner, or richer and richer and richer, and then see at what point the flame refuses to propagate, right, and then you now obtain the limit. But this experiment will also depend on the diameter of the duct below a certain value of the diameter, right. So above a certain value of the diameter, then the flammability limits that you determine become insensitive to the diameter of the duct. But now we have to think about the effect of the diameter of the duct. So flammability limits are influenced by duct diameter at low pressure, I should say below a certain value, right, at low pressure. So what this begins to mean is the duct diameter below which you are going to have a flammability limit being sensitive to the duct diameter is going to depend on pressure. That means lower the pressure, higher would be the duct diameter below which the flammability limit begins to become sensitive to the duct diameter, right. So this is typically at lower pressure. There are two things that can happen. One is the difficulty in ignition, or quenching, right, or quenching. That means if you could ignite, it would quench, or you would have difficulty in igniting to begin with, right. So you get into that regime where you have this problem, and this is typically in both the cases difficulty in ignition or propensity for quenching. This is because of heat loss to the duct. Heat loss to the duct. So we will consider this a little bit more detail next. First let's consider quenching. It's a little easier to deal with when compared to ignition. Quenching. So as the duct diameter decreases, right, a minimum diameter exists below which flame cannot propagate, okay, at given pressure and temperature. Right. So this is mainly due to excessive heat loss to the duct walls. So for the sake of simplicity, instead of taking like a tube or a duct, we could just consider like a channel or two walls, two parallel walls, right. So adopt a 2D geometry, adopt a 2D geometry for simplicity to think about this. There is parallel plates. So if you now think about right, that looks like parallel plates, doesn't it? So we are now thinking about a flame that is trying to propagate within this region, and it is releasing heat QR dot from the chemical reactions, and it is giving away QL, that is the loss. So this R is for release and L is for loss to the walls, right. And the distance between these two plates is dq, q for quenching. So we are essentially looking for the quenching distance here. So at quenching, what we have is two things. One is q r dot, the rate of heat release, which is phi naught q r w dot and a dq. So a dq is actually the volume, and a is like, let's say, the area of the plate. If you can consider a certain area in this, and we will see that it doesn't matter. We are going to ultimately look at what happens per unit area. So so for whatever area, the area times dq is the volume over which you have the heat release that is going to the heat that is released that is going to get lost, right? So correspondingly, if you now have a ql dot, this is actually heat lost by conduction. Right, and this is, I'm going to say approximately, for a reason that will become very apparent right away. We have two walls, and so you start with 2 area times k. Now let us suppose that the temperature gradient can be replaced by a linear expression. That is where the approximation comes from. Strictly speaking, we should say dt by dx at the wall, and look for a temperature profile between the walls and look at the gradient at the wall and so on. But what we are essentially saying is TQ is the quenching temperature, in the flame. That is to say, if you now think about like this propagating downwards, for example, you have reactants here, and the reactants are supposed to be heated up to the flame temperature, but that could actually happen probably near the center of the flame, and you could have a fairly higher temperature that is reached for the products. But on the sides closer to the walls, the reactants are not getting heated up all the way to the adiabatic flame temperature, because you now have heat loss. Therefore the temperature that is actually attained for the products is now not going to be really Tf like a adiabatic flame temperature, rather it's going to be Tq. Okay, so there is a temperature distribution that's happening across, and what we are looking for is like a quenching temperature. That means you need to have the reactants raised at least up to a certain temperature beyond which it can actually have appreciable reactions going on, right? So in other words, you now try to have a flame held near the wall, you will find that there is still a standoff. That means you don't have reactions happening right at the flame. Okay, and what this really means is in this standoff, the temperature is actually increasing from the wall temperature to like a TQ within a very, very short distance, maybe about a few millimeters or less, and that means you now have a reasonable temperature gradient between the wall and the standoff distance, which is going to now feed this heat flux, and that is the reason why the wall is getting heated up. If the wall were at a high temperature to begin with, right, then you won't have too much heating. So in fact, this is one of the reasons why you need to think of it. Typically these are all things that people have to bother about if they are setting up experiments, because experimentalists are the ones who are going to deal with, I mean, most experiments are on steady state problems or oscillatory, even if it is transient. Very, very few people are actually doing experiments on quenching itself, but those people who are interested in actually having steady state flames in their experiments want to make sure that it doesn't quench, right, or want to make sure that the walls that they are actually using in the experimental setup when it's subjected to flame doesn't melt, right. So typically what's happening is, if you now use like a ceramic wall, for example, right, it is an insulator, so it doesn't really take away all the heat, right. Instead it's actually getting heated up by itself, and it's increasing its temperature, and because it's increasing its temperature, this difference comes down, and therefore you have less heat that is going in. That's typically how insulators work. It's a heat transfer thing. The only thing is we have to make sure that the insulator is able to withstand the temperature to which it is raised so that the conduction is decreased, and that ceramic does that job for you. Therefore that's how it works. Otherwise if it's like a metal wall, it's going to get heated up progressively because of this, and it's going to stop the flame of a rise in temperature, right? And there is like a limit temperature that you should be thinking about, beyond which you're not going to have any appreciable reactions. Similarly, phi naught here is of course the stoichiometry that is how much of the fuel for a given amount of air is reacting. QR of course is the heat of reaction, and W dot is the reaction rate, let's say assuming a single step reaction, or essentially putting together QR and W dot, we are looking at what is the chemical heat release rate, these two together, right. So so now if you say at quenching we have QR dot is of the same order or equal to QL dot, then you now put these two together, you're going to get, of course the area cancels, therefore we should have been looking at per unit area to begin with. So dq squared is equal to dq squared is equal, you have a 2 here and a 2 at the bottom, therefore you get a 4k tq minus t naught divided by phi naught w qr. But qr is equal to Cp Tf minus T naught. This is as if, you know, what we are thinking is approximately you have a temperature profile that is inclined linearly near the walls and reaching up to Tf in the middle, okay, and it's stopping at around Tq there, and then from there you're now having a heat loss. So this is like a bulk analysis, we are not looking at the spatial variation in the temperature. So you would like to think that the flame is actually having a flame temperature Tf up to which you need to have the heat release heat it up, but that heat is now going to go away from a value of Tq to the wall temperature by conduction as a loss. Therefore if you now plug this in, you now get, so this is an approximate analysis of course, and I'll show you where the approximation comes from as we go along in comparison with experimental data. So if you now say 4k divided by phi w times Cp Tq minus T naught divided by Tf minus T naught. So we have alpha, the thermal diffusivity is K divided by rho naught Cp. Rho naught is the upstream reactant gas density. So we see that dq is proportional to square root of alpha divided by W dot. Doesn't it look a bit similar? I mean, have you seen this somewhere, right? Obviously we know that SL goes as square root of alpha W dot, right? So we had something like square root of kW dot divided by Cp, that's how it was going, and you had a 1 over rho naught outside the square root. So if you now put that together, you will now have something that's going as alpha W dot. We have seen this also before, okay. So if you now put these two together, then what basically remains is SL dq is proportional to alpha, and that is to say alpha, I mean alpha is like a thermophysical constant for the material. So what this basically means for you is dq is alpha over SL, or in other words, larger the SL, right, lower the quenching diameter, right. What that means is if a flame is going to propagate fast, it's going to go through a duct which is of a smaller diameter. That means you need to have a still smaller diameter for quenching the flame, right. So that simply means that the flame is trying to propagate more vigorously and you need to squeeze it into a smaller duct, right. To give you numbers on how this works out, so for typical hydrocarbon, fuels between parallel plates, dq is around 1.8 millimeters, right, and you can look up the actual values for, let's say, circular ducts in the literature for exact fuels and so on. There is these things are catalogued, and that is pretty important for you when you're trying to devise experiments on premixed flames. For example, you want to make sure that the flame doesn't flash back from where you want to stabilize it in your experiment, or if it does, then you need to be able to quench it before it actually gets to the source, right. So many times in experimental setups you have something like a settling chamber into which you would mix your fuel and oxidizer or fuel and air, and then let it through a duct into which you want to stabilize this. And if you have a flashback, the flame can go all the way down and into this settling chamber, and this settling chamber is now like a constant volume combustion region where it can actually explode. And we have had a couple of such things happen in our labs, right, when students aren't really careful enough. I shouldn't say that. They go through calculations on having a small array of tubes to actually quench the flame as it tries to propagate. If it is not a good calculation, the calculation is wrong sometimes, or they have made some assumptions or put in incorrect values, like on the flame speed, for example. If they're doing calculations for a phi that's equal to 0.7, but actually they turn out like depending upon how the sequence in which you close your valves at the end of the experiment, you might locally get into a stoichiometric mixture that propagates faster, right, and it can go inside, right. So typically you're looking at capillary tubes, like stainless steel tubes that are about 2 millimeters in diameter, and then you now try to stack them up in an array, like in a hexagonal close packed structure kind of thing, so that you form like a honeycomb thing, and you now insert it in your inlet, and this acts not only as a flow straightener for the flow that is going into this duct from the settling chamber, but it is also, more importantly for us, from a combustion point of view and from a safety point of view and from a quenching point of view, it's acting as a flame arrestor. So this is what's called as a flame arrestor. Typically in crude Bunsen burners that you want to put together, you would also have something like metal balls that are thrown in there, small metal balls, such that the voids between the metal balls are of this order. Or you could also put some steel wool, just crimp some steel wool and then just pack it inside. This will also straighten the flow. It's like a porous medium, and also arrest the flame from propagating upstream, right. So these are all typical approaches to flame arresting based on the idea of quenching. Of course, what happens is there are lots of applications where it is, I should say, for example, there are these applications where you want to have some nice uniform heating in some place, like in gas heaters, where you want to try to heat, and like room heaters or water heaters in large furnaces and so on, or large boilers. You want to have like a very nice uniform way by which you want to stabilize the flame without getting into turbulence and so on. So there is like there is an array of lot of small ducts through which you could actually send in fuel and stabilize the flame, because flame stabilization is a big issue, right. So when you now get into turbulent flames, trying to stabilize the flame with a larger duct may be difficult, so you actually use smaller ducts. And at that time you could even think about like a porous plate or these very small fine ducts into which you can send in this and stabilize the flame. That means you have very small lots of tiny premix flames that are stabilized on these. And the question there is, you could still stabilize the flame if you're having a sustained ignition to begin with, and you now heat up this array of ducts, right? And once the duct is heated up and the temperature is now higher, then it's going to be able to sustain this. So there, this difference comes into picture, right? So you're now trying to increase the wall temperature with the flame itself for some time, and then the flame will sustain there without really getting quenched or flash back and quench, right? So such things are done in practice in some applications. The next thing we should think about is ignition. So at this stage I should state a couple of rules of thumb, kind of criteria for ignition, which you will see works the reverse of the flame extinction that we have been talking about. So Williams, this is actually following Williams rules of thumb criteria. Ignition, and reverse holds good for extinction, right? The first thing is, if you now imagine like a slab of gas, slab of reactant gas, we are now beginning to talk about ignition. That means you don't have a flame yet, right? So you have to now think about a slab of gas that's approximately equal to the flame thickness, right? And you need to have an ignition source that now in a sustained manner increases this temperature of this reactant gas up to the flame temperature, right? So that is the criterion number one. So the ignition source should raise the temperature of a slab of reactant gas of thickness of the order of the flame thickness to the flame temperature for ignition. So you can see that if you now already had a flame which had a flame temperature, then this really means that the temperature has to be brought down from that value in order for it to get quenched, right? That is what we were talking about as the difference between Tq and Tf, and you can see that it is not going to be as low as T0, which is the initial temperature or the temperature of the wall, right? So obviously the ignition is not going to work exactly the same as quenching, and that is what I was beginning to say. I guess I didn't really pursue that so far. When you're now saying that you have dq is going as alpha over SL, right? It's not just this dependence that matters. What is the coefficient, right? The coefficient is actually coming all the way from these things, right? And what I would like to point out is you had a 4 sitting here. In reality we are using something like a dq over 2, that is like half the distance is corresponding to a heat loss to one plate, half the distance is corresponding to a heat loss to the other plate, right? Then there is something called a notion of a heat loss penetration. So the idea that we have used here is the penetration distance is equal to half the quenching distance. That means the penetration of the heat loss is equally from both sides all the way up to the middle is what we are saying. But empirically if you think about this, this is not really 2, it turns out to be actually more than 2. That means you don't necessarily have to have a large penetration distance. Okay, you don't have to actually have a penetration all the way to the middle of the of this. This is significantly larger than 2. Okay, so you're not going to get something like 4. It could be much more than that. We are okay on an order of magnitude, but this could be like, for example, 8. If it's 8 and like it's about off by 4 times, you see. So for 4 or 5 times is typically how this is going to be. So as a first cut, we would like to think this is what it is, but you don't need to necessarily penetrate that much. Even a little bit penetration of the loss, the heat loss, is sufficient to actually bring down the temperature to like a TQ, which is going to quench this, right? On the other hand, the ignition is now going to require for you to actually heat up the temperature significantly. It's not like a small loss in temperature that causes quenching. It's going to be a significant rise in the temperature by ignition source for you to be able to ignite. So this is as a first criterion. The second criterion is on the heat loss. So the rate of liberation of heat, here when you're talking about ignition, we talk about liberation of heat instead of loss. So the rate of liberation of heat, I'm sorry, this rate of liberation of heat is about from the chemical reaction. So by chemical reaction, I meant to think of rate of liberation of heat from the ignition source, but when you try to ignite, then you need to initiate chemical reactions because of the increase in temperature meeting the first criterion, and thus the heat released from the chemical reaction inside the slab, the same slab that we are talking about, must approximately balance the rate of heat loss. Let me just use this other panel. Rate of heat loss from the slab by conduction, right? So it's a very similar idea as what we're thinking. We will pretty much use these kinds of expressions, but I would like to show you through a little bit more rigorous analysis, just a little bit more, not significantly rigorous, more rigorous, but this is like a global heat balance, if you will, right? We are not talking about a spatial variation, but if it's possible for us to actually think about how locally the temperature gradient is going to get set up, right? And so that means you use like a dt by dx instead of having this kind of a linear expression for the temperature gradient for a global temperature variation. You now try to actually look at how the temperature variation happens and take that into account for the heat loss, and then that means we now have like a derivative, like you have to worry about a dt by dx, and then that means we can integrate that and so on. So let's do all those things next class.